All right, so let's start back earlier. Right. Lastly, we decided to talk about radioactivity. Right, we talked about radioactivity, right? We talked about alpha, beta, and gamma particles. And we said that we described properties of each one of them, right? Right, we described properties of all of them. I did not do a decay equation, so let's just do one real fast, right? Right, let's say you have that push-ups. Right, let's say you have that reaction there, right? You have Re undergoing an alpha decay. So it will lose a helium particle. And Re undergoing a beta decay. So it will also lose an electron. See if you can figure out what is X and Y, please. Just a quick review on what we did last day. What is X and Y? Right? So remember, you have to make sure that the mass numbers, of the reactant is the same as the sum of all the mass numbers and product. Same thing with the atomic number. Try that one. Find X and find Y. What in minus and minus one. All right, so we'll end up with what we'll get. We'll end up with so for the mass number, it will be 212, and then we could minus off the 4 and minus off the 0, and we should get X. So X is what? 208. Yeah, all you get that? Yes, sir. And then Y is what? 92 minus 2 minus 1, right? So that'll give us plus 1. So that's 92 minus 1, 91. Yeah. So that's a quick look at how to balance the equation, right? Right. Let's move on. Oh, I didn't do this experiment as well. How is what's the device used to detect radiation? Yeah, sorry. It's called what? Yeah, what is called the device used to detect radiation? Yeah, GM tube, right? So the GM tube is used to detect radiation, right? And before you get a count rate, that's this value here. Before you get a count rate, what's the first thing you do? So before you get a count rate of the radiation, what's the first thing you need to do? Find something. Find the, before you bring in the radioactive sample, right? There is something you have to find first. You have to find the background radiation. Oh, somebody said that? Oh, sorry. So you have to find the background radiation, right? So the background radiation gives you an idea of the radiation value before you bring in an actual radioactive source. Okay? So remember, in any question that asks you to find a radioactive, to find the radioactive activity, you need to find the background radiation first, right? Okay, nice. That's something I wanted to point out here, right? Right, a very special property of radioactive elements is called the half-life. So the time it takes for a radioactive element to go to half of the present value, right, Josiah, is called the half-life. Okay, so for example, let's say we have a mass of an initial mass. Let's say the initial mass is 200 grams, and it takes 2 days to experience its half-life. Then after 2 days, the new value is how much? 100 grams. After our next 2 days, which is 4 days, it will be, and after our next 2 days, it will be 25, right? Right, and then after our next 2 days, it will be 12.5, right? So what you will recognize is here is 1 half-life, here is 2 half-lives, here is 3, and here is 4. What we could also do is represent this by a fraction. So 100 is a half of the original value, 50 is 1/4 of the original value, 25 is 1/8, 12.5 is 1/16, right? So to figure out the number of half-lives, there is this nice little formula here, right? There is this nice little formula here, 1/2 squared, 1/2 cubed, 1/2 to the power of 4. 2 cubed is 8, 2 squared is 4, 2 to the power of 4 is 16. That formula gives you an idea of what the half-life is. So you see the power here? That gives you, how much half-lives went. Okay? So there's 2 half-lives here, 3 half-lives went here, 4 half-lives went. All right? So let's say the fraction is 1/32. How many half-lives went? Nothing there. I didn't put it up. Keep moving. Give it a little bit to cool down. Right? 1/32 is how much half-lives? 5. So that'll be 1/2 to the power of 5. Okay? That's 5 half-lives. So the formula is 1/2 to the power of n. Right? Right, Dylan? That will give you the fraction left. Okay? That will give you the fraction left after n half-lives. That's okay? I'd like to also give you this graph. What is called that graph? It's called the decay curve. Right? It's called the decay curve of a radioactive element. That's okay? Michael? That's okay there? Right? So that is called your decay curve. Nice. How do you find half-life from a decay curve? Right? You're going to have to take 3 readings and then find the average. So if you watch here, I showed you how to read off the 3 readings, right? So your first reading is here, your second reading is here, right? You come here and read off here. How you find the half-life? You subtract those 2 answers. To get your second reading, you take this value here, subtract them. That'll be a third half-life. And then take this value and this value, that'll be a third half-life, add it up, divide by 3. Okay? So graphically, to get half-life, you need to get 3 readings. All okay with that? And last thing, right, is Einstein's energy mass relationship, right? So watch here. Right, I just want to run through these steps and finding the energy given off in a reaction. Right, so watch here. So if you look here, if I were to give you some reactants, right? If I were to give you some reactants, and those reactants obviously will give you some products, right? What Einstein said is that there's a change in mass during this reaction, and as a result, energy is given off. That energy is given by mc squared, right? So we need to learn to find that energy. To find that energy, all we have to do is find the mass of the reactants, the mass of the products, and subtract them. So your first step is to find the change in mass. That's the mass of your reactants minus the mass of the product. Okay with that? Problem is that this is sometimes in U, right? So if this value is in U, atomic mass, second step, you have to multiply by 1.6. No, it may just be 1.66, 1.67, right? 1.66 by 10 to the minus 27 to get the value in kilograms. That's okay? So step one, work it out, you get it in U, convert to kilograms by doing this. It's the second step. So your third step, to find the energy, you take in your delta M in kilograms, that's this value here, and multiply it by the speed of light squared. 3 by 10 to the 8 squared. Right? So those are the 3 steps in finding your energy involved in a reaction. Right? You find the change in mass, so you add up everything here, and minus them. Should be a small value. Right? If the value is in atomic mass, multiply it by 1.66 by 10 to the minus 27. Right? Then multiply it by 3 by 10 to the 8 squared. And that will give you the energy. Okay? This is the energy given off during those nuclear reactions. All right? And the answer is normally where? Around what? The answer is normally, the energy is normally around 10 to the minus 10 to minus 13, somewhere there. Right? So it's 10 to the minus 10 to around 10 to the minus 13 joules, right? So normally is around it, normally, right? There are times that we could be smaller. Right, make a note of the steps. Right, we need to know about what is a fusion and what is a fission. A fission experiment is where you have one big nucleus splitting up into smaller nuclei. Are you okay with that? Fission is a big to small. Fusion is small to big. Right? Here are 3 uses of radioisotopes. There are many more, but it's just 3. Carbon dating is what? Finding the age, right? finding the age of, well, ancient artifacts, something, treating cancer, right? Why it is we can use radioactive isotopes to treat cancer, right? Because one, it can destroy the cells, but the reason for that is that radioactive, like gamma, for example, radiation has a high penetrating power, right? So it can penetrate through the muscle and it can find the cancerous cells. What's the next property? What's the next property of radioisotopes that allows it to be a good tracer, for example? What's a property? We just kind of talked about it a little while ago. Not here, before that. Right? If you put a radioactive element in here, do you want it to stay forever? No, you want it to come out as soon as it finish, as soon as it finish use it, right? So because of it, because it have short half-lives, like a day, half a day and thing, right? That's one of the reasons why we could use radioisotopes. Okay, so because of the varying half-life and because of the penetrating power, we could use it for some of these things, right? Right? So that's it. We have fission, we have fusion, and we have the uses. All right, let's go one time, cross papers. Let's see where I have this again. Saturday. John, let's start here. John. Let's start with John. Right, fill the table out fast. Fill the table out fast. See which alpha, which is beta, which is gamma. Right, sadly, today's radioactivity and magnets. So we'll do the theory and magnets today and probably do a couple questions. What's the first one? Alpha, beta, or gamma? Next one. And last one. Oh, yeah, fill out the rest. Right, stop by what? Gamma is stop by. Right, the range of air. Alpha is travel of you. And beta is stop by aluminum. Isotopes are what? Same atomic number, different mass number, right? Nice. Next one here. Work out the mass number first. Yeah, mass number is how much? 11. Right, the mass number is 5 plus 6, 11, and the atomic number is 5. Nice. Let's go. Next one. What's a possible isotope of element Y? Element Y was 11, 5. What's a possible isotope? 12, 5, right? 12, 5. Or even 10, 5. All right. Isotope, you just changing the mass number. Hurry up, balance those two and find the half-life. Well, find what they ask you. Balance those two.
Everybody get with mom.
Right, so it's forming lead, right? It's forming lead by alpha alone. Right, that's it. So it is minusing what? Minusing 4 from 210, that's 206. And then you're minusing 2 from 84, which is 82. Nice and easy, right? Go again. Go again, they give you the half-life. Right, to the next part fast, they gave you the half-life. And they said a certain sample contains so much, right? So that's at the beginning. What's the number of nuclei after 552? So you have to figure out how much half-lives in there. All right, so let's see what happened. So 552 divided by 138 is how much? Is how much? 4 half-lives. So it means after 4 half-lives, that'll be 1 on 2 to the 4, which is 1/16. So the amount remaining will be 1/16. But they asked for the number, right? So that's 1/16 by 6.4 by 10 to the 6. How much is that? Sorry? 0.4 by 10 to the 6. Nice. That will be nuclear, right? Let's go again. Any more here? No, that's it. Any questions, Olia? Soraya, you okay there? Nice. All right, have a next Soraya. But you okay? All right, good. Come on board, right? Next one. What year was that again? All right, let's move on. Let's check out 2022 June. Right, Roy. Remember, you forget to pay for the crash course, huh? Roy? All right, we'll have to come in and check Roy. Roy didn't pay for the crash course. Huh? The one in the blues, the one with the iPad in the back there. Oh, shucks. This one had a radioactivity, or was number 1 or? Oh, yeah, number 1. Right, so, all right, we'll skip, or should I make it bloody graph, right?
Yes.
Yeah, who say no? Right, me? Right, help me out here, me. Right, Kumar, what would the shape look like? How? Right, do you have a curve like this? How you find half-life? Right, 3 different regions, right? So you take here, half of it, that'll be a first half-life. Then you find half of this, that'll be a second half-life. Half of that, third half-life. Okay? Don't forget. All right, nice. So they would ask you that, right? Okay, so that's June 2022. Let's check out Jan 2020. Oh, I don't have that. All right, let's check out Jan 2021 then. I've Jan 22 somewhere else. Next one. This is June 2011. Sorry, June 2021. Right? Name the two scientists. Name the two scientists that that assisted Rutherford. Geiger, Marsden. Geiger, Marsden, right? You should be able to spell it as well, right? Right? Geiger and Marsden were the two guys who helped Rutherford in his lab, right? Explain why the experiment was carried out in a vacuum. Why was it carried out in a vacuum? Huh? Right, no air resistance, and to reduce the particles losing energy. And you don't want the particles colliding with anything else, right? You only want the alpha particles colliding with the cold foil. If it had air, it might collide with the air particles, right? Okay, so you want no other, you want the alpha not to collide with anything else. Right? And you don't want to reduce energy loss and so on. Right? Well, they label it up here, right? There's the next question where they ask you to label it. Say the conclusion for each one. Most of the alpha particles pass through. Conclusion is the atom is mainly empty space. A few of the alpha particles were deflected. The core was small and positive. Okay? Deflection indicated that they core positive as well. So it might be nice to write that. Might be nice to write it. Might be. Huh? Pardon me? Deflection indicated that the core was small and positive. Should we show you which year? You walk. Come on, sit down in front of me. Right? And last one, they use the word rebounded, right? Remember, I use the word reflected. So what happened if a small number was rebounded? It meant that the core was what? Dense. So it confirmed that the core was small, but it also said that the core was dense. All right? Describe the Rutherford model of the atom based on the conclusion. Huh? So you had to kind of put it all back together. Right? Rutherford said that it had a positive nucleus with protons and neutrons. And yeah, small and dense. Yeah? Part 2, it was small and positive. So you getting around that? All right, and the Rutherford's model said that the core was a nucleus. The core was the nucleus with protons and neutrons, right? Now it's positively charged, surrounded by electrons, right? Surrounded by electrons and shells. He didn't really just cover that. He had put it all together. Next one, you have a reaction here to do for me. Do that, please. You have to find the energy In fact, they actually change in mass, not the energy. Oh, yeah. They ask the energy after. So I'll leave it here, right? Do the reaction. Do the reaction and then find the energy. Right? All right. Do the reaction, balance the reaction. That is one over, yeah, a neutron. Yeah, it's a neutron. So in the reaction above, what symbol is the alpha? For 2 helium, right? So you got to balance it. You just need it in the next part. Oh, you're gonna be going there. On the right, So they give you the reaction there, you know what the reactants are, what the products are, right? Right? Everything in you, right? All the values in you, so you have to convert it. You not seeing it? You not seeing it? Write down the equation, right? Everybody write it down. Right? You don't have to write, just write the equation first. Write the equation first. For those who are not seeing it. The number's not too important. It's balanced already. Right? And then I'll leave it here, right? Yeah. The question is to find the energy. Just work out the energy. The first part is to find the change in mass in kilograms. Second part is to find the energy. So take the reaction and find the energy. So you see that now, right? Yeah. On that one side is that one side is helium on the right? You have to follow it. That's like it, right? Right, so you're following these steps I gave you, right? Everybody getting the values, right? I'm taking it off, right? So watch here. Here you have your reactants. So you have to find the mass of your reactants. You have to find the mass of your products and then minus them, right? So these are your reactants here and these are your products here. And these are your products. Right? So to get the change in mass, you have to get the mass of the reactants and minus the mass of the product. So I'm going back to the question there. Right. So the reactants are what? The reactants are helium and beryllium. So that would be I know rounding up 4.00260 plus beryllium. Yeah, you gotta write the whole thing. 9.01212 minus the mass of the products. Products is 1.00867 plus 12. Right? When you subtract it, that value is in U. How much you all got there? Huh? No, in U.
Yeah.
No, 10 minute final answer in U. No, in U. Before you multiply it. Yeah. So 0.00. Yeah. So that's the value in U, right? But we need to convert from U to kilograms. Are you okay with this? First step, reactants, products, minus it. And then you want to convert the kilograms, so you multiply by 1.66 by 10 to the minus 27. Convert each one to kg. Yeah, you can do that, but that will take a little while. And then what? How much is this here? 1.00 by 10 to the minus, right? 29. So that value in kilograms, right? And now you want to get the energy. Cover it. Right? How do we get the energy? The energy is the change in mass by the speed of light squared. All right. So you have your change in mass here already in kilograms, and then multiplied by the speed of light squared. 1.0043 by 10 to the minus 29. Right? And then multiply that by 3 by 10 to the 8 squared. And the answer should be by 10 to the minus 11 or 12 or something, right? Yeah, somewhere around there. How much you got? 9.0. 13. Right? When you reach everyone, you can round off, right? So that's the energy involved in the reaction. What year was that? Let's go again, June 2021 now. Huh? What year was that? Jan? That was Jan 2021. This one telling me June, Harry. Make sure you tell her that, I'm sure. 2005. I don't have that here now, right? What you do it already? Right, try this one here. Hurry up. Nalia, our space in front here. Nalia, in the back. You'll always talking more. If Nalia, if the distraction, I'll bring you here, right? What's she answering? Oh yeah, it's Nalini, sorry. Okay, let's go. First part. Protons is how much? Online, wait. I find online real quiet. Chelsea, are you okay there? Emily? All right, press that all again, should I? Right, protons. 88 protons. Neutrons is what? Neutrons is? Right, 226 minus 88 is? 1. Number of electrons. Right, number of electrons is the same as protons, right? 88, right? What? Or what? Or you can figure that out. Huh? Huh? Oh, persistent. Next one. 226. A 226 nucleus decays by alpha emission to radon. Explain what is radioactivity. What's the definition? Spontaneous decay of a radioactive. Radioactive element, right? Spontaneous is important, right? Balance is so fast here. Complete the equation for radium. Remember, right? It became radon by alpha decay. Underwent alpha to become radon. Hurry up. Write that out fast. You guys should do it. Sure. Do it again. I have to do it again. Huh? Yeah, alpha decay. Right, so it's 4.2 here. And the mass number is how much? Right? And the atomic number. Nice. Let's go again. Wait, you all got that? Everybody get that, right? Right? Write down the half-life, write down what it is, and write down the half-life of radon. What's the definition? Right? Time taken for half of the present element to decay, right? Time taken, in the summary, time taken for half of the present element to decay. Underline present, right? Don't leave out that at all. Write down the half-life too, please. Yes, write down the value. You need it for your next part. Next one. Try those two parts there. Let me just same thing, right? Not really much about it. Much. 10 to the 8. Half-life is 1600 years, right? Right, question after the number of alpha, right? So every radon that decays gives you alpha. For every radon you have one alpha, right? For every radium, sorry, produces one alpha. Every reaction is every radion that decays. But if the idea left but two, right, that was left with how much produce. Pasa ya, So we have a little problem here, right? The question asks us for alpha emit. The question asks for alpha emitted. If you go back to your equation, you would see that you'll see that every radon that decays. Sorry, it's radon or RA? Every RA that decays produces an RN and an alpha. Question asks us how many alpha emitted. So for every one that decayed, every radium that decayed produces an alpha. So we have to figure out how much radium has decayed. So let's see. After 4,800 years, that is how much half-lives? 3 half-lives. So therefore, the fraction left is 1 over 2 to the 3. But we are more interested in the fraction decayed, right? Because only if we know the amount that decay, we can figure out the alpha, right? So if 1/8 decay, sorry, if 1/8 left, then the amount that decayed is 7/8. Okay? So the number of alpha will be equal to 7/8 of the original amount. So that'll be 7 by 10 to the 8 alpha particle. All right. So this was slightly different, right? You have to realize that every radium that decays produces alpha. So the answer would not be 1 by 10 to the 8, it will be 7 by 10 to the 8. Are you okay with that? So the fraction, the formula that they give us, will give us the fraction left, right? We have to figure out the fraction decay. So 1 minus that, right? Are you okay with that? So you have to look into the wording and see exactly what they're finding, right? What they're actually finding. One last part underneath that. Underneath they ask, how much more time will elapse before the radium nuclei reaches 0 by 10 to the 5, sorry, 0.5 by 10 to the 8. How much more time? The key word there is more. Right? So think about it. How much half-life to reach 0.5? How much half-life to reach 0.5? One more, right? So to reach from 1 by 10 to the 8, to go from 1 by 10 to the 8 to 0.5 by 10 to the 8, that's the next half-life. Or you can do it like this. Or you can do it like this. 0.5 by 10 to the 8 over 8 by 10 to the 8 is 1 over 16. That's okay? Which is 1 over 2 to the 4. So it will take 4 half-lives to reach here. Right? But the question asks how much more time, right, after this. So 4,800 is 3 half-lives. So it means to reach 4 half-lives is plus 1 more half-life. So the final answer is 1,600 years. All right. So basically to go from 1 by 10 to the 8 to 0.5 by 10 to the 8 is 1 more half-life. All right. Let's squeeze in one more now before we start magnets. Are you okay with that? Yeah? Sure. So the wording in that question was a little tricky, right? Last one, Jan 2020. Right, if you don't have it, just send it here, right? Start there. Where is the alpha, beta, and gamma going? Remember I showed you left hand rule to work it out? So work out where the alpha going, where the beta going, where the gamma going. Hurry up. I'll try this now. I send if you decline it. All right, so where alpha going? Right, if you use the left hand rule, right, magnetic field going in, the force going up. So your top, your middle finger should be pointing out outwards, and it going to the left here. Gamma going straight through, and the beta going to the right. How to use the rule? All right, watch here. Watch here, right? So if you have left hand rule, right? Remember, let me tell you board. Right? Those who are online, you also watch it. Go to the camera, right? So you have an alpha particle going outwards, right? And we're gonna do this now anyway, right? Alpha particle showing in the direction of a positive charge. Left hand rule. So your magnetic field is X, so that's going in, right? This moving up. So I'm gonna turn it upwards. So therefore the forces that way then. Who should middle? No. Like that. Right? So it's looking like this. Are you okay with that? So therefore the alpha particle will experience a force going to the left. All right. And if you figure out alpha, then beta will go this way, gamma will go straight through. Yeah. Are you okay with that? Right? Left hand rule, right? Should we see the middle finger in class? All right. So now you should talk to your father. You still are joking, boy. Go ahead. Next one, electric field. Who going where? Who going where, Olia? Alpha going where? Alpha going towards the negative, beta going where? And gamma going. Always remember that the alpha will have a longer path, right? That's okay? The alpha has a longer path all the time. Don't forget that. Next. Oh, you have an equation to balance here. You have some reading to do. Read that fast. It says 2020. Read it quick, write the equations, and then you have a calculation here. Read it quick. For the 20. Oh, that's not score already.
Do this. I'm going to do so far.
I don't do any from this book.
Well, I want you to do these booklets. These will have answers, so I can trust they actually try it.
Yeah, I'll do that tomorrow. It's physics, so that's not after physics. You're correct on everything.
All right.
Huh? Nah, can't zoom anymore. All this zoom in finished there. No more zoom available. Oh, should we just see, man? All right, which part? So the first is a beta decay, beta then alpha, right? That good there? That's okay there? Hidesh, you doing it? Hidesh, every time I watch you like teaching or not doing it? Come on, do the work, please. Huh? You want in the back? There's just Hidesh? D-base, sure, D-base. Wait, where Hidesh going? You going outside? Huh? Hey, boy, hey. Be quiet now. Right, first one is what? Lead, so it's 21082, and the lead, right, undergoes exactly 2 beta decay. So beta is 018 to become what? The mass number stays the same, and the atomic number is now what? Right, which one there is 83? Bi, nice. And then Bi now undergoing what? Bi undergoing no, beta again to become 210 what? 84. 84 is what? PO. And then, but I'll just squeeze in the last one. 210, 84 PO, losing an alpha, right? To become what? 206, 82. Everybody okay with that? You just minus in the values, right? And 206, 82 is lead. Sorry? What's that? Yeah, any pacemakers here? Probably I think it have a very long radioactive half-life, right? So now let's take it out. And last part before we start magnets. Try that, please. Right, for those who not seeing it, the values they gave you is 0.3018 U. They gave you the mass defect. Huh? Nah, not today, last day. 0.3018. Huh? Yeah, I'll give you Easter Tuesday. Hello. I extended it. Right? 0.3018, and they wanted to find the energy. Hurry up. Right? Follow the steps I give you. Josiah, hurry up. Find the energy.
And I thought
Yeah. Right, look back. Ah. Yes, so I know. Oh yeah, got it fast enough. I think if you did not. Now give it a little 2 minutes and then we'll start magnets, right? So it's doing anything else. The last part is doing everything. Yeah, so Rafa. All right, just correct that and
Oh, damn. Well, use a gram plus. A gram plus. You know the function.
see. Last thing here, 0.3018 multiplied by, how much you got there? 988. And then you want to find the energy. So the change in mass by the speed of light squared, right? So that'll be 5.00988 by 10 to the by 3 by 10 to the 8 squared. 4.5.
Yes, I get it.
Right? I can no math, you know, how you working? What's my work today? The formula, I substitute, I do everything. All right, take a 2-minute break, then we start magnets. Because today is magnets. And I give all the extra time before I start.
From the time you get from outside, break down the hierarchy.
Yeah, 2 minutes doesn't go anywhere. Oh yeah, 2 minutes to pee and come back. I started magnets. Huh?
That's the point. Just no, that's great. Yeah, and
All right. Just before we begin, right? When is maths again? I know you all tell me date. I want to make sure I have the right date. Maths is what date again? 17th. And physics is one. And maths. But if I examine the 12th or the 11th to me, in the morning, or it's 3 o'clock. So it'll be done by 3 o'clock. It'll be done by about 2:30, 3. As the maths all night, that's the same night. Well, if I examine the 15th. All right, let's begin. Magnets. All right. So, no simulation. Right, so I'm going to try to explain most of the things in magnets, right? Ready earlier? All right, let's begin, right? Who must start? Oh, you want? All right, good. Hey, all ready? All right. So you want to start with magnets. We start firstly with a simple bar magnet. Right? A simple bar magnet has what? A north pole and a south pole, right? How do you figure out the magnetic field around a bar magnet? What you use? A simple, right? A simple plotting compass, right? And the plotting compass will give you the direction in magnetic field. Magnetic fields always leave the north and go towards the south, right? Right? Magnetic fields always leave the north and go towards the south. Here, where you have plenty magnetic field lines per unit area, right? That's where your magnetic field is strong. And the word that they use sometimes is magnetic flux, right? Magnetic flux is the number of field lines per unit area. That's okay? So, right? So magnetic field lines always leave the north, go towards the south, and the number of field lines per unit area is called magnetic flux, right? What do we know about light poles? Light poles repel, right? So the magnetic field lines will not interact. So they would move away, right? Okay with that? And in the middle, there's a region called the what? Neutral region, right? Most of this in the summary, I just going it over. All right? Right? And so light poles repel, unlike poles attract. So the magnetic field moving from north to south, north to south, north to south. Right? So there's an interaction, I'll pull it in together. Are you okay with that? Right? Next thing that we need to know, if you have a current carrying conductor, right? Something carrying current in it. Let's say you have current going into the whiteboard, or you have current coming out of the whiteboard. Then you could use right-hand rule, right? You could use the right-hand rule to determine the magnetic field lines around here. Okay? The right-hand rule is, right? Your fingers point in the direction of the magnetic field, and your thumb points in the direction of the current. So your thumb is current, and your fingers point in the direction of the magnetic field. Okay, so let's check it out and see. This is in, X is in, right? And the dot is out. Okay, so you're going in, and your fingers pointing in a clockwise direction. Okay, so the P lines here are clockwise. Right, the P lines, they are clockwise. Right, it's going in, so it will be in a clockwise direction. Coming out now, coming out will be in a anti-clockwise direction. Right, Dylan? Okay. We also need to remember that both of them represent poles. Okay. The one that moving clockwise, south pole. The one that moving anti-clockwise is a north pole. Okay. So in is a north, out is a, sorry, in is a south, out is a north. Are you okay with that? Yeah. If I give you a flat, a flat coil, a simple flat coil, again connected to a supply, current coming out here and current going in here. Okay, so current going in here, I can use this so I can figure out what the P lines will look like, and current coming out here, so the magnetic field lines will look like this. Right? So if I have a flat circular coil, right, that is one coil alone, the field lines look like that. Are you okay with that? Yeah? Everybody okay with that? So you have to be able to draw the field lines, right? That's a flat coil. Next one is if you have a solenoid, right? A solenoid simply means this. A solenoid simply means right, a few of these. So you have current going in at the top, coming out at the bottom. In at the top, right? You'll see that? So going in at the top, if the current is here, it's going in at the top, and it's coming out here. In is an X, and it's coming out at the bottom. That's okay? So what you have here is a solenoid. So you could draw a solenoid like this or like this. You have to figure out now the magnetic fields around a solenoid. So you're going to use Fleming's right-hand rule. Sorry, right-hand rule again. Okay? Right? So you're going to use this right-hand rule again, but you have to flip it around. Right? You have to flip it around. The thumb points towards the north, and your fingers point in the direction of current. Right? So we're using the right-hand grip rule twice. We're using it to find the magnetic field in a flat coil and also in a solenoid. Okay? So here's how it works. It going in at the top, coming out at the bottom. So your hand going in and then coming out. You're seeing that? Watch. So your fingers going in at the top and then they're coming back out at the bottom. and your thumb points towards the magnetic. Thanks. Right? And your thumb will point towards the magnetic north. So it means that here is north and here is south. And we can come back here. Magnetic fields always leave the north and go into the south. Are you okay with that? So once you figure out north, you know where south is. And you can connect them if you want. Right? Everybody okay with that? Right? Here's what we're going to do next. We're going to take a current carrying conductor and put it in the middle of a magnetic field. Right? Remember, this has a magnetic field. Right, Elena? This has a magnetic field and this has a magnetic field. Whenever two magnetic fields interact, what will happen? You'll either get a attractive force or a repulsive force. That's okay? So we're going to take a current carrying conductor and put it in a magnetic field and see what happens. Huh? You want to eat it? Microwave right? Sure. All right. So here's what we're looking at now. We are taking a magnetic field and we are going to put a current carrying conductor in the middle. So we're going to use Fleming's left hand rule, right? The left hand rule is used to find force and the right hand rule is used to find current. This is called the motor rule, generator rule, right? Motor and generator, right? That's okay? Motor, generator, force, current, right? Huh? All right, ready? So we're using the left hand rule, right? So you have your thumb, your first finger, middle finger, right? Thumb is the force. First finger is your magnetic field, and your middle finger is your current. Okay, so let's start. The magnetic field moving where? North to south, right? So the magnetic field moving from north to south. Dot means what? Dot means out. So your thumb pointing where? Upwards. So this conductor will experience a upward force. Right? Sometimes they have to draw the P lines, right? Here's how it looks. The reason it gets pushed upwards is because all the P lines underneath here, right? They form a kind of an elastic effect. So all of them come close and they push it upwards. Okay? So the magnetic P lines look like that. All okay with that? Yeah? Let's try the next one now, just to make sure. Magnetic field lines always what? Always go from north to south, right? Try that. See if it's up or down. Left hand, eh? What you all got online? Up or down? Online? What again? All right. I'll put it on them there.
Yeah, right.
Right? Ready? So the magnetic field is where? North to south. X means what? In. X means in. So therefore your thumb pointing upward. Up. One more. Last one. Up, down, left or right. Up, down, left or right. Right? Right? There you go. So magnetic field going down north to south. Magnetic field going north to south. Current coming out. So the forces. Oh yeah, to the right. Wait, do happen. So learn one and that's rotate. Right, so you can do as Dari said, right? You can learn it and rotate the book and work out all the rest. Right? That can work too. Right. So this allows us now to move into the motor. Right? Because the motor is you apply a current in a magnetic field on a conductor and you'll get force. Right? So all the motor will do is take a coil, current flowing coil, and allow it to experience a force that will cause it to turn continuously. All right. So you have to be able to explain that. You don't really have to draw it. So I think I've seen a question where you have to draw it. Right? So normally just give you a little diagram and you have to label it. Superior, I superior, we can do this whole thing here. Right? What chair you don't want to get number? Where just go? Oh, okay. All right. Huh? Okay. Oh, that's right. Where's go? One out? Who's go fast now? Let's go. All right, ready? So what we have here is a simple diagram of a motor, right? How you know it's a motor? What are the two main things that allows you to identify as a motor? Right? It's split rings and the supply. Right? Because a motor takes electrical energy and gives you mechanical energy. Okay? So it takes this to give you this. Right? Movement here. All right? Good. First thing first. We have to figure out current direction. Right? Positive terminal, negative terminal. So therefore, here is what? Positive here. So current flowing how? Current flowing up, down, right? That's clockwise. Right. before you explain, you have to label your rectangle coil. Magnet, coil, split rings. What is this here? Carbon brushes, right? Carbon brushes on your supply. That's okay? So you do a little labeling. You have A, B, C, D. Right? So in an exam, these are the first two things that you do. They give you a diagram, you tell them what direction current flowing in. Right? Current flowing A to B to C to D. Right? And of course, you must have it labeled. All right. Next step. Next step in the explanation. So step 1 in the explanation is your label. Step 2 in the explanation is to give them current, direction. Right? That's step 1 and 2. Step 3 now. Step 3 is where you use Fleming's left-hand rule. Right? So we're going to use Fleming's left-hand rule to give direction of movement. Okay? So I want you to try to tell me what direction AB is moving in. And then you can figure out CD. Right? Apply the rule, everybody. Apply the rule. You have current direction, you have magnetic field. Right? Yeah, force field current, right? Force field current. All right. All right, so what's here? What's here? Right. Right, Soraya.
Yes.
What direction AB moving in? Try it. Huh? Try it. Left hand rule. Current going where? Current. Current going up. Magnetic field moving. Magnetic field moving north to south, right? So line it up. Right? Magnetic field north to south. Current moving up. So the force is where? Inside. Well, yeah, do it relative to this. Right? So the current moving up, magnetic field north to south. Right? So therefore your finger pointing inwards. Are you okay with that? Right? Whenever you're doing it, draw it in your book. Draw it in your book and do it relative to your book, right? Otherwise, you'll get the opposite direction. So if I do it here, magnetic field is north to south. So this finger pointing north to south, middle finger going up, right? And the thumb going inwards. So AB is down. Huh? Right, so watch it again, right? Magnetic field north to south, current going up, right? So watch this here. Yeah, according to this, it's going up. So it's going up. So my thumb pointing into the whiteboard. Well, yeah. So I'll call that down, right? So it's going down here, and it's going this side going down and this side moving up, right? Not the best, right? But in words, you will write AB is moving downwards and CD is moving upwards. What's that? Right here. Yeah. Right? So therefore, AB going down, CD coming out. Are you okay with that? Right? So it's moving in a one direction. So it's moving like this. Right? If you draw it in a 2D diagram like this, it's moving anti-clockwise. You're seeing that? So it's moving like this. Right? And here's a downward force, and it's moving like that. Are you okay with that? So it's moving here, moving down, here, moving up. So it's moving anti-clockwise. Right, but you're not done there, right? So you're using Fleming's left-hand rule to determine the direction of motion of the coil. And then, right, what happens to the coil? What happens to the coil when it's horizontal? When the coil is horizontal, you see this here? This moving too, right? When the coil is horizontal, here's what's happening. Right? When the coil is horizontal, this will move like that. Okay? So the split rings do not touch the crush. So if it's not touching the crush, what will happen? No current will flow. Right? So something has to happen. And remember what's happened? Inertia. Right? Because you have a moving object, it won't just stop there. It will continue to move. So inertia, so you step 4, you have to use inertia, right, to explain continuous motion. Okay with that? So you have to use inertia to explain continuous motion. So when the coil here and the bridge here, you have to say when the coil is vertical, no current will flow, but because of inertia, it will move to the opposite side. Right? And then step 5, you have to say in step 5, current still flows. Current still flows in a what? Right? Current still flows in a clockwise direction. Right? Current flows in a clockwise direction, so therefore the coil moves. Coil moves anti-clockwise again, right? So I'll just try to give you 5 quick steps for you to explain the motto, right? Don't try to learn a paragraph or try to understand the 5 different things. Label, current direction, left-hand rule, talk about inertia, and then say the current in the same direction, right? The current will always move clockwise, right? That's the beauty of these split rings. Are you okay with that? So that's the motto. Let's shift now to generator. Take a little minute to eat the brain there. And then we do the generator. Generator has Faraday's law, Lenz's law. All right. So let's quickly look at Fleming's right-hand rule, Faraday's law, Lenz's law, and transformers, right? Are you ready? Right, so last thing, we're looking at electromagnetic induction. Electromagnetic induction is where you're using magnetism to induce electricity. So you're using magnetism to produce electricity, right? So now we're going to use Fleming's right-hand rule, right? Fleming's right-hand rule, right? Right-hand rule simply means exact same thing. Thumb is the force. Your first finger is the magnetic field, and your thumb is the induced current. Right? The reason we're using induced is because it's not there. Right? So we're using induced current. All right? So you're using Fleming's right-hand rule in the same way. So let's see, right? Right-hand rule. We have magnetic field, north to south, Soraya, north to south, and the force pointing what? Downwards. Okay? And so you're trying to see what direction your middle finger pointed in. Try it now. Try and see what direction your middle finger pointed in. Same thing, you're just using your right hand. Right? Same thing, but you're just using your right hand. So what you will tell me is, do I put an X or dot in there? Right? And what you will notice, it is not the same as what you did before. I'll explain why in a little while. Right? So watch here. Magnetic field, north to south. Right? Force is where? Down, right? So I have to turn this downwards. And you, right? And your middle finger pointing what? Outwards, right? So the answer here is a dot. Right? How come this is different? Anybody remember the explanation? How come this is different to what we had in the motor rule? Huh? Something else. Remember lens? Lens said all the causes. Anyway, I explained lens just now, right? But that's the reason why, right? Right? Because the induced current is always opposite. Try here fast. Last one. Try here fast. Try this last one here. Right hand. Right, so let's see. Right? Right hand rule. Right? Right hand rule now. Magnetic field moving north to south. And the force is where? Away from me. So the middle finger pointing in. So what do I write? Right. Right? So what I'm saying there. Right? What the right hand rule is saying is this. The right hand rule is saying is that if you apply a force in a conductor in a magnetic field, you will obtain a current. That's okay? So if you take a Oh, by the way, a generator is the same thing except for what? No supply, right? And it have slip rings. Okay? And there's there's no supply, you have a voltmeter here. Right? So it's very similar. All you're doing is you are applying a force and you'll obtain a current. That's okay? Looks the same. You have slip rings and you have a voltmeter here. Okay? Right. I want to show you one more law. And that's it, right? Right, and then we will squeeze in a couple of past people. Or one, let's squeeze in one. All right, so let's take a look at two quick laws, right? Let's take a look at Faraday's law and let's take a look at Lenz's law. Two more laws, right? Olha, we here, Aria. Not supposed to learn it. Right? So you still need it. If you look at 20 something, the same thing came. Right? Exact same law came. Right, quickly, how these laws work is this, right? If you have a conductor, like a solenoid, and you have a galvanometer here, right? If you take a magnet, around the magnet, there's a magnetic field, of course, right? That's okay? If you take this magnetic field and put it inside here, right? Once this conductor here cuts these lines, you will get a current reading. And Faraday said that the faster you take this magnet and move it in and out here, the greater is the EMF. Right? That's what Faraday said. So the faster you move this in and out, the greater is the reading. So the galvanometer will give you a larger reading the faster you move it. That's okay? And it's the same principle. Same principle, right? You're moving something in a magnetic field and you'll get a current. That's okay? All okay with that? Lens is a little harder, though, right? Lens a little bit harder. Huh? The faster you move the conductor, the bigger is the reading on the galvanometer. Right? So the faster the field line cuts here, the bigger is the voltage of current. And Lenz's law a little bit harder. Here's what Lenz does, right? Lenz gives us an idea of the direction of the current. Okay, so watch this here. Here's what Lenz said. Lenz said that the direction of the induced current here always opposes motion. Okay, so watch this here. If your magnet's moving inwards and you want to create a pole here that would oppose this, what pole will happen here? A north pole. And so a north will oppose a north, right? And when it's moving out, a south will happen here because the south will pull it back in, right? So the north will oppose the north and the south will also oppose the north when it's moving out. All okay with that? So when it's going inwards, you have a north here and you have a south here. And you come back to these rules, right? And you'll come back to these rules here, right? So you have a north here and current is what? Current coming out at the top, out, in. All okay with that? Current coming out at the top and going in at the bottom. All right? So it's coming out here and going in here. So it might look something like that. Coming out here and going in here. That's okay? Coming out and then going in. And the galvanometer will follow it. So the galvanometer, the arrow here will follow the direction current. So if the current going this way, the galvanometer goes that way. Okay? What will happen, Arya? What will happen when the magnet coming out? Here becomes what? Here becomes a south, and here will be a. So what will happen to the current direction? It will change, and the galvanometer will go in the opposite direction. Are you okay with that? That's it, right? And before, let me just finish up. We have one device that uses this electromagnetic induction. It's, well, not one device, the next device, because it also have this speaker and it have the generator, right? But the next device that uses this is called the transformer, right? You have an alternating supply here. You have a voltage supply. That's with primary, right? You have a voltage primary. You have a number of coils primary. You have a voltage secondary, number of coils secondary. What's the formula that brings all this together? NP over NS is equal to, right? And last thing, if the transformer ideal, what you do? Right? Right? Power in the primary is equal to power in the secondary. And you will get this nice formula here. VP on VS is equal to IS on I. All right? Make a note of that. That's your Magnus summary. Okay? That's the magnet summary. Let's do one question and then I'll do some more next tomorrow, and then we start tomorrow will be electricity, right? I will switch it. I'll leave waves to the last thing. Waves is the longest. Huh? Yeah. I'll leave waves to last, right? Ready? Right, let's try one fast and we're done, right? Right, label up fast. Oh, I didn't tell you what B was. Anyway, we'll figure it out here. A is what? A is the primary coils. B is what? Right? I forgot to tell you, there's a soft iron core, right? Soft iron core. Right? B is the soft iron core. C is the what? Alternating primary supply. Right? C is the alternating primary supply. And D is the what? Secondary coils. Everybody okay with that? Identify the type of transformer. Right? right? When you have less coils to more coils is a step up. So it's a step up transformer. So your voltage should be what? Your voltage in your secondary should be higher. Say the formula relating V and N. Hurry up. What's the formula? Right? Write it fast. Write it fast. Next part. A transformer has 500 turns in secondary. 5,000, sorry. 50 in the primary. And they gave you the voltage supply to its primary is 12 and current is 6. Find the power. Well, I was supposed to show you that in electricity, but power is what? How you find power? Well, we do have work done. IV, right? IV, right? So current in the primary is I by V. I is how much? I was 6 and the voltages. So that's 72 watts. Right? They want the voltage in the secondary. What's the formula we're going to use now? Shibish? How we going to get voltage in secondary? Shibish? Right here, Shibish. Right? So you're using NP on NS is equal to VP on VS. So you can rearrange it and you will get NS VP over NP. Are you okay there? And just plug in your values. That's what, 50? 50 by 12 all over 5,000. How much you got? 0.12 what? Volts, right? What type of transformer is this? A step down, right? So the value okay there. Last part. Find the current in the secondary if it's 100% efficient. If it's efficient, what does that mean? Efficiency means no energy loss, so power in the primary equal to. So we know the power in the secondary is also what? 72. Hurry up, find current fast. And we're done. Find the current fast and we're done. Right, so try and go over this tomorrow. We'll do some more magnets and then we will start electricity. Electrostatics and electricity. How much you got? P over V is equal to what? 72 over. How much is that? 600 amperes. All right, nice. That's it there.